Hi, I'm Rui Pereira da Costa, organizer of the NO Masters 2015. I'd like to present you my friend and colleague José Aranguren from Spain. Apart from being #1 fan of Real Madrid football team, José is an associate professor of the postgraduate program in endodontics and restorative dentistry at the University Rey Juan Carlos of Madrid. He had his specialist degree in endodontics and specialty certified in Endodontics University of Southern Mississippi. He has more than 40 articles published in national and international journals, many of them about one of his favorite topics, instrumentation systems and endodontic files. His lecture will be about a very innovative instrumentation system that was commercially launched not so long ago. Hope you enjoy.
Hello, good afternoon. I'm José Aranguren from Madrid, Spain, and it's for me a real pleasure to do this lecture in this great online event. Thank you to Rui Pereira for the invitation to do this lecture here. It's for me an honor and a pleasure to do it. Welcome to my lecture in this EndoMasters 2015. The topic is going to be about instrumentation, how files work inside the canal, what problems we can have while performing the treatments, and also about ProTipper Next, a new system that is changing our work in the office.
What are we looking for an endodontic file? We look for an easy instrument to use and also to learn. We are looking for an instrument to have a good performance into the canal with a nice shape, low risk of complications, also like complications like fractures and canal deformation. And we are looking also about systems with no many instruments, only with few instruments. This is important also because if we have many instruments, the system is going to be more expensive, so the cost is also important, and also is important the ergonomy during the treatment. Manual shaping is the most common way of shape the canals, but it has several difficulties, like problems during the instrumentation, like thip, canal blockage, canal transportation, apical extrusion, time consumed, less predictable in shaping, and too many instruments. These are the main important difficulties during the shaping with manual files. So we recommend for this reason to use nickel titanium rotary or reciprocation instruments. We can reduce the time in shaping, we can do predictable shapes into the canal. It's really easy to use the instruments, and we are going to achieve better results. With the manual files, like in this study done by Sergio Cutler, we can see the difference between shaping with a profile or with a manual file. In the left hand we have the shape with a profile, and in the right hand we have the shape with a manual file. We can see the difference between both. If we change this to another way of canal instrumentation, we can see the difference between profile and anti-curvature system of shaping done by Abu Ras. In the left hand we have again profile, and in the right hand we have anti-curvature shaping style. We can see the difference between both, always profile center better into the canal. Here we have the difference between profile and balance force shaping. Balance force is the best one with manual files, but we can see also here the difference between profile shaping and balance force shaping into the canal. Here we have a root canal treatment. We can see how we treat the canal, how we finish the case, and we can see the case is okay, but we have a small canal transportation in the mesial buccal root. This is due because when we use, here is the place, when we use the manual files and we shape with manual files, it's really easy using so many files, so many steps to do a small canal transportation. We can do this also with nickel titanium files in rotation or reciprocation, but in my opinion is more difficult to produce this kind of canal deformation with rotary or reciprocation files. In 1991 we have the first rotary nickel titanium instrument in endodontics, and from that point to now we have thousands of different systems. We can buy it in Europe, others only in America, others in the other part of the world, and we have so many systems, and in this moment we don't know which system is the best to use. We have so many in the market, and it's difficult to choose which one is our best system to use. In conclusion, for all of this, I can tell you that all the systems are okay to shape canals. We can shape, doing a great shape with almost all the systems we have already seen over there. But the most important difference between all of them is that you can choose to use more taper, less taper, stiffer instruments, more flexible instruments. We have to use the system we are more comfortable with it. The variables in the performance of the mechanical instruments, the main variables are section, the alloy, the file size, also diameter and taper, the movement, rotation or reciprocation, anatomy with curve, length, width of the canal, and in the last point, compressibility. The section is the main part of the file because it's the ADN of the file. The section is the variable that change the performance of the file into the canal. The alloy is also important, and in this moment is one of the most important changes we are having in the manufacture of the nickel titanium file. This is changing a lot. We had a few years ago the change from standard nickel titanium to N-wire, and now we are changing to have new alloys like the gold treatment of the new Majefer and Dentsply file. The file size is also important because the size of the file is going to change the performance of the file into the canal. If we have a bigger diameter, the file is going to be stiffer than a file with a smaller diameter. And the taper in the same way. When we have a bigger taper, we are going to have also a stiffer file. So we have to change these 2 points to have flexible instruments into the canal. We can't shape properly a curved canal, a really curved canal, with a big taper or a big diameter file. The movement is also important because we have the standard choice of shaping in rotation and the new option since 2 years ago to do reciprocation to shape the root canals. The anatomy is also important because it's not the same to shape a straight canal than to shape a curve or a really long canal, and also it's not the same to shape a wide canal than to do it in a really narrow canal. All these 3 points are important when we are shaping a root canal. In the anatomy, we have 3 variables: curve, length, and width of the canal. Both 3 are really important because if we find or we have to shape a canal with one or more than one of these variables, the shaping is going to be harder. We can also find a canal with 2 or 3 of these variables. This is going to be a really tough shaping. When we use a file in one of these variables, a curved canal or a long canal or a really narrow canal, we have to know that the amount of cycle fatigue earned in the file or the torsional stress is going to be really high. So maybe we have to think that file is going to be a single-use file. In some canals, we can have more than one variable. For example, we can shape a really long canal, a really curved and narrow canal. So in these cases, this is more important. The file is going to suffer a lot. Is going to have a lot of cycle fatigue stress and torsional stress. So for sure, we have to use that file just single use. The compressibility is another important point. Is the quality of a file to have a performance like a spring. This is really important because the file has resilience, and the performance like a spring makes the file more resistant to torsional stress. In the history of nickel titanium starts in 1991. In this year, we had systems with passive radial lamps, with fixed tapers, with just one cross section, and most of the systems in this moment were systems with many instruments, as light speed system, for example. In 2001, this was a really important year because was the beginning of ProTaper, the actual universal ProTaper. It has active cutting edges, also variable tapers, and just one cross section. Most of the systems had from 4 to 18 instruments. 2007 was another important date because it was the introduction of new alloys. In this case, the system GTX came to the market with a new alloy called M-Wire. Also, in the same year, Cybernendo developed also a new alloy called Airfast. This is really important because it's the future, in my opinion. The future changes in the design of new files will be in this point, in the new alloys development. In 2010, we get 2 more files, a new motion, reciprocation motion, and these 2 systems were thought to use in the canal as a single instrument for shaping the canal. All the instruments were with different tapers and also with different cross sections in all the surface of the file. In 2013, we continue with the new alloys with the M-Wire, in this case with ProTaper Next, and also a new design in the file, a quadrangular cross section off center, and it was also important the introduction of a new system called adaptive, with an adaptive movement. It means that it goes in rotation, and when it needs, it goes also in reciprocation. The future, in my opinion, would be new files, maybe done in polymers, the continuous working in new alloys, looking for new alloys to improve the performance of the file in the canal, and maybe structures like the system we already have in the market, SAF, similar files to this one, to try to get to more part or more surface of the canal. It's a good idea, but maybe they have to improve the system a little bit. Here we can see a tooth, and now with a few instruments we can get a nice shape as we are having here, and the new files, the new systems improve a lot the shaping, and we can get that with just a few files. The only contraindication of rotary nickel titanium files is that they can break, and we have to take care of this, and we have to know when can this occur. Nickel titanium appears in endodontic in 1988 with Wally and students. It's a crystalline phase austenitic that is resistant, but when we pressure and heat the crystalline phase, it goes to another phase called magnetic file, where the file breaks. Here we have a diagram when we can see the initial part of the austenitic phase, and this is the plateau. This is the point of elastic deformation, and here is the break of the file. The principal difference between the steel and the nickel titanium files are that with the steel, when we bend the file is going to keep the bending. With the nickel titanium files, when we bend the file, we are going to recover again the straight of the file, because it's a shape memory. Here we have a nickel titanium file, and F1, when we treat with cold the file is going to keep the bending, but when the file recovers again the temperature, the file is going to, with its shape memory, to become straight again. Here we can see also a video about nickel titanium. This is a wire of nickel titanium, and when we put it in hot water, it recovers with its shape memory the first shape of the wire. Here again also. Here is another wire. We can see the wire here. We are going to treat it with heat in one point, to create a 90 degrees curvature. And when we have the wire and we heat it again, it recovers the shape. Here with a can also, we put the wire around the can, and when we heat it again, it recovers the shape of the can. The superelasticity is affected by the presence of a residual deformation, which increases as the percentage of deformation increases. The factors that promote this deformation are related to the presence of small precipitates of titanium and nickel and the formation of an error phase transformation that prevent full martensite during the transformation phase. This performance decreases the fatigue strength of the nickel-titanium alloy under cyclic loading. This is also important because when we are using a file or reusing a file, the file accumulates precipitates of nickel and titanium, and this is why the file breaks for cycle fatigue or for extended uses. Here we have the graphic, and we can see when we use a file here, when we finish using it, we use the same file again, and we stop using it. We use the same file again, and you can see when the file starts here, the next time the file doesn't start at the same point. This is because the accumulation of precipitates of NiTi and titanium in the file. This is the cycle fatigue of the file. Here we can see a tooth, and we can do a treatment perfectly without many effort with a few files. Now we can do a good shape to create a great taper to do a nice treatment. Here we have the file to working length, and we can see when the file is at working length, because of the shape memory always is trying to get straight, so is making load against the exterior of the curvature and also in this point. So when we are using a file, this is more important when the file is bigger. When we are above 25 or 06 taper, we need to do this really carefully, because with a small file we can use it without any problem. But when we have a big file, the shape memory is going to be bigger, and the force the file is going to do against the canal wall, so this is the transportation of the canal, is going to be bigger. So we have to take care mostly when we are using bigger files. We can see also this article. This is also interesting because when we work with a file and we do too much pecking motion, going inside, outside, we can transport into the canal also. So the two choices are not to be too much time at working length, and the other one is not to do many pecking motions when the file is going inside the canal. Here, for example, we have a treatment, and we can see here a canal transportation, maybe because the person who did this treatment was with a big file, too much time working at working length, and because of the strength of the file, they get the transportation. Here we can see also 3 different plastic blocks done by GPs, the standard dentist, and we can see depends of the file they are working or depends of the system they are working, they can get more or less canal transportation. This is important because the big difference between the systems, with any system of the market, we can shape perfectly the root canal and we can do a good treatment. But the big difference between the systems is there are some systems that they are easy to use and it's difficult to create a ledge or a transportation, and other systems you can work with them perfectly, but they are more difficult to work with, so we have to take care for not making any transportation or leads into the canal wall. Here, this is a study, a research we did a few years ago. We compare protipper universal, M2, reciproc, and wave 1 in plastic block. We dyed the canal, and after that, we did the treatment and we compare both canal shapings. Here we have the 4 systems. Lately, we add also the protipper necks, and we found no difference between the 5 systems. If we shape properly the canals, we can do a perfect preparation with any system. The big difference, in my opinion, is that some of the systems are really easy to use and it's difficult to create a problem, and others we have to be carefully because they can create a canal transportation or whatever. Why the files can be stiff? Because the section, because the alloy, because of the pitch. When the pitch is much bigger, the file is going to be more stiff. Also because of the size of the file, the diameter and the taper, and also the compressibility of the files. This is a characteristic really important that we have found in protipper next. Section is really important because it's the ADN of the file. With the cross section we have, if we see the cross section, we can know how it's going to be the performance of the file. If we have a big core, a big cross section, the file is going to be stiffer, it's going to have a better performance with the torsional stress, but it's going to have a worse performance with the psychic fatigue stresses. We can see also the edges of the other files. We can see most of the new files have active cutting edges to have more efficiency during the treatment while they are working into the canal. Here we can see a test done by Elio Peruti. It's interesting because we can see here 3 path files, the 13, the 16 and the 19, and we create a curve, so they are having a big psychic fatigue stress, and the first one who is going to break is the bigger one, because we know in curves the psychic fatigue is more important when we have a bigger core, a bigger cross section. Is the opposite when we go to a torsional test, because in torsion, when the file is smaller, the performance is worst, and when the file is bigger, the performance is better. Here we have also another point is the alloy. The alloy is really important in this moment. We have different changes in the alloys of the files. Here we have, for example, the N-wire. The N-wire has 2 good points. The first one is more flexibility in the file and also more resistance of the file to psychic fatigue. Also a diagram where we can see a diagram of standard nickel titanium, and here a diagram of N-wire. We can see how we can improve the resistance of the file till the break in the martensitic phase. This is also a really important article. This article is from Eugenia Johnson. It talks about the same instrument in 2 different designs, one without N-wire than just in the standard nickel titanium, and the other one in N-wire. And the difference is 400% higher resistance to psychic fatigue with N-wire. Also, we have the air phase. The air phase is from Cybron Endo, and it's the same. More flexibility in our files, and also extended time before fracture in sake fatigue. We have here also another study that talks with air phase treatment. The files are more resistant to sake fatigue. Here we can see also a test done by Ben Johnson. It's interesting. We have 3 different shafts. The first one, nickel titanium. The second one, nickel titanium with electropolish. And the last one done in N-wire. We can see the first one is a standard nickel titanium. The second one is the electropolish shaft. And the last one is the N-wire. The N-wire resists a lot of more time before break than electropolish and standard nickel titanium. We can see this also in this graphic. We can see at first a standard nickel titanium, then nickel titanium with electropolish, and in the last row the N-wire that is a lot of more resistant to sake fatigue test. Electropolish, we have some articles like in green that agree that is better a file with electropolish than without electropolish because you have a better resistance of the file. In red, we can see that there is not important difference between having electropolish or just a standard nickel titanium, but the real thing is if we look for it in the literature, we can find that there is not many difference between a standard nickel titanium and nickel titanium with electropolish. We can see here a few pictures in the right side with electropolish. Here this is an interesting article that talk about electropolish. We have 4 different systems. We have Profile, Race, K3, Aero, and M2, and they did the comparative between both 5 systems. They found the more resistant system in sake fatigue is the Profile because it's design. So this article concludes that it's more important the design of the file than the electropolish of the file. There is not many difference between electropolish or not electropolish, and is higher the difference when we change the design of the files. Here we have also that with electropolish we decrease the efficiency of cutting of our files. So if there is not many difference between electropolish or a standard nickel titanium and we decrease the efficiency of our files, we think electropolish at this moment is not really important in our design of the new files. Here is another study we have already done in the university. We took ProTaper Next in 2 wires. These are files ProTaper Next X2 done in a standard nickel titanium, and we took the files we can buy to use with patients that are done in N-wire. So it's exactly the same design, an X2, but only change the wire. We have a standard nickel titanium or we have the N-wire. We did a sake fatigue test, as we can see here, with our machine, with our Eastern machine, and we use the 45 degrees curve, and we test our files there. We found a really extended time before fracture with the N-wire design. A really huge difference, almost the double time before breaking than with a standard nickel titanium. We can see here the graphics and here the results. Almost the double time before breaking. So it's a huge difference in our opinion. It's not 400% as in the article of Eugenia Johnson, but is the double. So it's really important, the difference. We can see here in time 3 minutes 25 against 2 minutes and 6 seconds. We can see here the diagram also. Now let's talk about the pitch. The pitch is also an important characteristic of the files because it changes the performance of the file depending the pitch. When we have a great space between the spires of the file, we are going to have a less flexible file. And when we have the spires really close one to the other, the files are going to be more flexible. This is important. We can see this in this article of Versulis. And it's important also this because when we are designing a file, we have to think in this important characteristic. We can see here the different files, and when we have the spires really close, the file is going to be more flexible, and when they are further, the file is going to be less flexible. Now we are going to talk about taper. Also, is another important characteristic. The taper is important because when we have a file, depending if we have a constant taper or just a variable taper in our file, the performance of the file is going to be different. With a variable taper, we can take high tapers in our files because we are going to use big tapers in the point of the canal where we want to, and we can decrease the taper in the rest of the canal to reduce the stiffness of our files and to have a better performance of our files inside the canal. When we have a constant taper, we can't reach a really big taper because if we reach to a big taper, our file is going to be too big and is going to be too stiff to work properly into the canal system. Here we can see the difference between a ProTaper, universal ProTaper, with really low taper in the tip of the file and a great taper in the coronal part. And we can see against a profile with a constant taper of 0.4 in all the file. Now let's talk about compressibility. Compressibility is a characteristic that we can find in ProTaper Next. It's the capacity of a file to performance like a spring. So the file has resilience, and this is really good because when we have, for example, a torsional stress, this stress is reduced because of this spring performance. This is really good because these files, ProTaper Next, reduce a lot torsional stress due to this capacity of compressibility. When we shape a canal, we can have a few problems. For example, fractures of the files, canal transportations, apical extrusion, and these mainly are the most important or more common problems in our shaping procedure. First, we are going to talk about fractures. We have two kinds of fractures: torsional fractures and flexional or cyclic fatigue fractures. We are going to talk first about torsional stress and torsional fractures. Torsional fractures are produced when a file is blocked in the tip and the rest of the file, the handle, for example, is keeping moving in rotation or reciprocation, and as the tip is blocked, the file breaks. This is really important when we have a really narrow, a really small file, and it's not so important when we have a huge, a big file. We can see here in these two files, when we have a torsional stress, we can have the unwinding of a few spires of our files. Here we have a file, we block the tip of the file keeps in rotation, an elongation of the file, and after the elongation we have the torsional fracture. Here we can see a study we did a couple of years ago with a torquemeter, and we compare K3 against profile in torsional stress, and we can see when we have a bigger file, always the performance of the test, the torsional test, is always better when we have a bigger file. It's not only bigger when we have a bigger tip or a bigger diameter taper. It's also important when we have a bigger cross section. In this case, we have a better performance of K3 because this file has a bigger cross section, and we can see always the 15 is always worse than the 20 or the 25 or the 30. So it's important the apical diameter, the amount of nickel titanium of the file, and also the cross section. Here we can see also another study. We are finishing about finite element analysis, and we can see here the comparison between the wave 1 and the protaper. We can see here in these two torsional tests, we can see a bigger amount of stress in the wave 1 file. This is due to the amount of nickel titanium. The cross section of wave 1 is a bit smaller than protaper, so this is why we have a bigger torsional stress. The torsional stress goes proportional direct to the amount of nickel titanium we have, or the cross section or the taper. When we have a bigger cross section, a bigger taper or a bigger apical diameter, the performance of the file in torsional test is going to be a lot better. Here we can see the flexional test. The flexional fractures are produced when we are in rotation with a file in a curve. The inside of the curve is with a compression, and the exterior part, the out part of the file, is in elongation. This goes with 300 rounds per minute, and this is going to create a break in the file. This is important because when we leave a file working, or when we place a file in a canal working at working length and we don't move the file is going to be curved in the same point. So in this maximum point of curve, the file is going to suffer a lot of flexional stress, and the file can break for flexional or sag fatigue. Here, this is a test we did a couple years ago about sag fatigue of different systems. Here we compare wave 1, reciproc, M2, and protaper universal, and we can see the difference between all the systems. We found the reciprocation systems have a greater sag fatigue resistance to breakage, and we can find here also when we have a bigger file, the performance in this test is worse than when we compare in torsional test. In flexional test, the bigger file is going to have a worse performance than a smaller file. A smaller file works better, have a higher sag fatigue resistance than a bigger file. Here we can see, for example, the comparison between protaper and M2. Protaper has a bigger core, a bigger cross section, so the performance is worse than M2. In flexional test, in torsional is going to be the opposite. So it's really difficult to find a perfect file, because if we have a great file in torsional test, it's not going to be really good in flexional test, and the opposite. We can see, for example, here the comparison between protaper and wave 1. Here we have a greater sag fatigue resistance of wave 1. Why? Because the alloy is en wire, and also because the movement is reciprocation, so the file is going to have a greater resistance. Here, for example, also the same, N2 versus reciproc, we are going to get a greater resistance in reciprocation with reciproc and with the alloy en wire. Results: alternative movement significantly better than continuous. The alloy is also important. Reciproc, more resistant in cyclic fatigue than wave 1 in 45 degrees, 60 and 90. But in 90 the difference were not really high. So this is why we think if we have to performance a test, a cyclic fatigue test, we have to look for a small curve, because when we have a great curve, all the files have a similar performance. Here we can see also an interesting article of Gianluca Gambarini, and we can see how always reciprocation has a greater resistance to cyclic fatigue test. Another one of Sehab. This is important because we can see also that when we are in reciprocation, we have less transport into the canal and greater cyclic fatigue resistance. But we can see also when we have a smaller angle in reciprocation, is also important. We are going to have a greater resistance in this case. So it's better for cyclic fatigue to have a 90-45 degrees reciprocation than to have it in 150 to 30 degrees. Now let's talk about apical extrusion. Apical extrusion is something many speakers use to criticize other systems. The most part to produce apical extrusion, in my opinion, is the way of shaping, the way we shape the canal. We, for example, can see this in this article done by Gustavo de Deus, how he concludes that reciprocation files or NiTi rotary files extrudes less than manual instrumentation. This is strange because, for example, we can see another article done by Sebastian Burklein. We can see in this article comparison of 4 systems, wave 1, M2, reciproc and wave 1, and they conclude that reciproc is the system with more apical extrusion. After reciproc, wave 1, and then the other 2 rotary systems. And in this article done by Javier Caviedes, they conclude that the result is that wave 1 is the file with more apical extrusion, and the file with less apical extrusion is reciproc. So if we see the literature about apical extrusion, is a complete mess. It's really difficult to find something. In my opinion, most of the articles are done to try to get a result. So, for example, in this article of Caviedes, we can see how he compared 2 files, the 4008 of wave 1 against the 4006 of reciproc group. So if we want a result, we need to compare pairs with pairs, apples with apples. So we have to compare the same taper, the same apical diameter. For example, it could be better, in my opinion, to compare the 2508 against the 2508 of reciproc. Here, which one is the result? So if you have a bigger file and this file goes at the same time, same speed into the canal, which file is going to do more extrusion? Always the bigger one is normal. So in my opinion, most of the studies are looking for a result to defend, to get the best result for their own system, the system they are talking about. In my opinion, the result, the apical extrusion, is always produced when we do a fast shaping. For example, if we go really fast to the apical third, instead to work first coronal part, medial part, and after that goes to apical part, if we go so fast direct to apical part, we are going to do more apical extrusion. That's for sure. So in my opinion, when we have a system that goes faster to the apical third, we can do more apical extrusion, but we can avoid this working first by parts, first in the coronal part, then in the middle part, and after that goes to the apical part. This is an article, and a study. It's not an article yet. We have a performance in the last month. We compare wave 1, reciproc, protaper next, and protaper universal. And we got that the systems that do more apical extrusion are the reciprocation systems. Why? Because they can reach easily to working length, so they can go faster to the apical third. This is not because they are worse systems. No, they are great systems, but they have to work first in coronal part, then middle part, and they need to avoid go so fast to the apical third to try to avoid the apical extrusion. All the systems with several files usually do less apical extrusion. Why? Because they go first working just in coronal part, then in the middle part, and after that they goes to the apical third. Here we can see that when we work with a big file, for example, this one is a 2506, and we leave the file working at working length, or we go many times in and out, like in the video, we can see we go in and out many times. We are going to do a canal transportation in the exterior part of the canal. And if we leave the file working at working length, also in the point of maximum curvature, we're going to go a high psychic fatigue stress, and the file is going to break also. When we have a big file, we have to avoid also to go in and out the canal many times. Why? Because when we go inside the canal, the file impact against the canal wall and bend. We take the file out, and when we take the file out, the file get straight. We go inside again, the file impact against the canal wall and bend again. We go outside, the file get straight. But all the times we are doing this back and forth inside and out the canal, the file is impacting against the canal wall. This impact made also a canal transportation into the canal walls. Here we have also a really curved case. How can we save a case like this? In my opinion, we have to avoid files with large section. We should escape from files with stiff alloys. We will try to do it in reciprocation or balance force, do it with our hands, maybe with nickel titanium files, but in balance force. Never in rotation, because when we work in rotation, we have a higher psychic fatigue. And we should avoid large taper also and large apical diameters. We can't finish a case like this in a 40 in the apical part, and we can't also shape this to a 8 taper, 10 taper, because the file with these tapers or diameters, these kind of files are really stiff. So we need a really narrow file, for example, a 4 taper, a 2 taper, something like that. And we should avoid also apical diameters above 25 or 30. Here we have the case. Also in this case is also important the obturation. In this case done with Gutacore. And let's see the next case. We have here another one, also curve. Here we have first to negotiate coronal part, coronal area, and we do not try to access too fast to apical portion. First, we have to work in the coronal part, and then after making bigger the access cavity, we can go to the apical portion. We have to try also to get a straight access to the canal, and also a glide path is useful in these cases because our files are going to go better through the canal without too much stress. In this case, above all, torsional stress, and because of the curve, also psychic fatigue stress. Okay, now let's talk about ProTaper next. In 2001, we get ProTaper. In 2006, we get ProTaper Universal, some change. And in 2013, we get ProTaper Next. ProTaper Next is a nice system. We can shape all kind of canals, small, big canals. We can get to tip 25, we can get to 40, to 50. So it's a really useful instrument. We can use it in all cases. Really small cases, wide cases, in all kind of cases. Here we have the files, the finishing files of ProTaper Universal, and the problem of these files were that they were really stiff. They were files with a big cross section, too much amount of nickel titanium, and this is not really good because, as I showed you before, when we place a file, a big file like these ones, in a canal, the file is trying to get straight, so it's going to do a transport outside of the canal. As here we have here a case, here another case, finishing here instead of where we want. This is because these files have a big cross section, so this big cross section makes these files really stiff. This is the change. Now with ProTaper Next we have a smaller core, a smaller cross section, so the file is really more flexible. Also, the change is that before we have a standard nickel titanium, and now we have NY alloy. As I told you before, this alloy makes our files also more flexible. So these files are going to be really flexible for two things, because of the cross section and also because the alloy, the NY alloy. Here we can see the section of ProTaper Next, and now we are going to show you also. We have here the section of arrow, for example, and now the section of ProTaper Universal, and we can see the difference, the amount of nickel titanium with ProTaper Universal compared with ProTaper Next. This is really important because when we have a really big amount of nickel titanium in a canal, we can have ledges transport into the canal, as we can see here in the plastic blocks. So we change a system with so many instruments like ProTaper Universal. Here we change this system for a new system with just a few instruments. Instead of 5 instruments, we can do mostly of the 80% of our treatments just with 2 files, with these 2 files, with the X1 and the X2. ProTaper Next is a nice instrument that works in continuous rotation. It has variable tapers, a smaller handle, just 11 millimeters, that improve accessibility in posterior teeth. We have 5 instruments, but in most of the cases, just with 2, with the X1 and the X2, we can finish the cases. All the files come pre-sterilized in blisters of 6 or of 3 instruments, and the use is intended single patient use. The section is a quadrangular section, a parallelogram, but the section is off-center. Also, as prototype universal, the taper is variable. This is really important because we can choose the exactly point where we want to have a big taper to work and decrease the taper in the rest of the file to have a better performance into the canal. All the files are done in NWire. The files work with ProTaper Next in continuous rotation. And as I told you before, the handle is soldered around 11 millimeters long. With this kind of cross section, this quadrangular cross section, we have a bigger space between the canal walls to remove the debris while we are working into the canal. So it's also interesting for this reason, this design of the cross section. Here we can see the file working. You can see how the file rotates. When the file is rotating into the canal, only 2 points of the cross section are contacting with the canal walls. This is really important because as the file is only contacting in 2 points, also is decreasing the contact with the canal walls, so it's decreasing also the torsional stress of the file, because with this contact just in few points is going to decrease a lot the taper lock while the file is working into the canal. The files are done in NWire that, as I told you before, improves flexibility in the files and produce a greater resistance to cycle fatigue in our files. Here we can see how the file is working, how the file, because of the off-center design, is also contacting in a few points that is going to decrease a lot the taper lock of the file. If we compare with a constant taper or with a normal file, the file is going to contact in many points in the canal wall. With the design of ProTaper Next, we can see that the file is just contacting in a few points. So, as I told you before, this is going to improve the resistance in torsional stress. I told you before this file, because of its design of the cross section, it has a really small cross section, so it has a really good performance in cycle fatigue test, but it's going to have also a really good performance torsional test because of this design, this off-center design that makes that the file only contacts in a few points, and this is going to decrease a lot the torsional stress of the file. So we have, for the first time, a file that is good in cycle fatigue test and in torsional test. We talked before about torsional stress, infinite element analysis. We can see here how we did it. We did it also with ProTaper Next. And we can see this is the design of ProTaper Next. And we can see, for example, here, I'm going to show you the torsional stress of Wave 1, ProTaper, and ProTaper Next. Here we block the shaft of the three files. We block completely all the core of the file, and we get the file with more stress. Gray is the maximum stress, then red, then yellow, then green, then blue. The maximum stress is in ProTiper because of the cross section. The cross section is the smaller, so the torsional stress is the higher. But which is the point here? When we work in a canal, we don't block the core of the file. When we work in a canal, the file is working, the active part of the file is working against the canal wall. In this case, as I told you before, ProTiper just contact in a few points. So this is important because if we repeat the same study, we can see if we block the active part, we can't block all the active part of ProTiper. So the torsional stress is going to be smaller here, not as smaller as in ProTiper Universal, but lower than Wave 1. In this case, Wave 1 has a smaller core, a smaller cross section, but due to the design of ProTiper decrease a lot the torsional stress because of the point contact it has. It contacts just in a few points, not in all the part of the file. So it decreases a lot the torsional stress. So in my opinion, it's a great design because it's balanced in flexibility, is balanced in psyche fatigue, is balanced in torsional stress. In my opinion, it's the first design balance in all the aspects of metallurgy. Here we can see how the file is swaggering, the movement. It's a bit strange because it's the first time with a swaggering movement. Critical path is also important because the difference between ProTiper Universal and ProTiper is that now all the files have a nice transit one to the other. Before, with ProTiper Universal, the change from the S1 to the S2 was too big. Now all the change from one file to the other are really similar, are really smooth. Also, the file is a bit smaller. Now we save normally to 2506 before to 2508. So with ProTiper we decrease also the shaping in the canal, and in my opinion in this moment we have to try to do this, not to do big enlargements, big preparations. In this moment I think we have to be soft with the canal and try to be conservative. In the torsional flexional stress, the results are really good, and this file is really balanced in both aspects, in psyche fatigue, in torsional stress also. The screen is also another important factor. With ProTiper we get a screen just of 1 Newton. With ProTiper Universal we get 2-4 Newton. So we decrease a lot the screen in the canal with ProTiper Versatility is another point important. With ProTiper we can do easy canals and also really curved canals. As we can see here in the plastic block with an X1 and X2, we are going to shape the canal, a really curved canal, a really difficult canal. The X1 can reach to working length easily without any glide path. This is not the best way to do it, but just for this case. And here we can see how the X2 goes easily also to working length. The problem is the person who is doing the block is going in and out so many times. We know ProTiper is a really flexible instrument, but in a really curved canal, a really flexible instrument, a really small cross-section instrument can performance also like a big instrument. So although the instrument is small, when we are in a great curve, the performance of the file is going to be as a big file. So when we are or just with a big instrument, or if we are with a really curved canal, we have to go with the last files just to work in length and out. Don't go in and out many times, because we are going to transport to the exterior of the curvature, or we can break the file for cycle fatigue in the point of maximum curvature. Here we can see also the space between the flutes. These spaces are important because we have bigger spaces with protaper necks, and here we can remove the rest of denting while we are working into the canal. Compressibility, I told you before about it, is the capacity of an instrument to be like a spring. So this is also important because the protaper necks performance as a spring, and this is also important because we can decrease also the torsional stress because of this capacity. So we get a better performance of the file because the cross section is small, because the few points contacting with the canal wall, we decrease a lot also the torsional stress, and with the compressibility we get also another point to decrease torsional stress. So we decrease flexional stress because the cross section and the design, and the torsional stress because the compressibility, and that the file while it's working is contacting just in a few points. So it's a really balanced design. Here we can see the 5 files: X1, X2, X3, X4, X5, 5 instrument sequence, but in most of the cases with 2 or 3 instruments is enough to finish the case. Length 21, 25, 31. These files are thought to use as intended single use, and the files can pre-sterilize in blister of 3 or 6 instruments. We can see here also the tips: 17, 25, 30, 40, 50, and also the tapers. Taper 4 in the tip, 6 in the X2, 7.5 in the X3, 6.5 in the X4, 6 in the X5, and then it's a variable taper, so if we need more or less taper, it increase or decrease to get a better performance of the file into the canal. You have here all the tapers also. The system comes, as all the systems, with paper points, gutta percha points, and also gutta core obturators. It's really useful to do it with it also. We can have the same obturator as the final file we have already used. So this is really useful also. This is the DUF of protaper necks. We have to try first with a 10 manual file to scout the canal. Then we get 2 pad files, the 13 and the 16, to make a glide path in the canal, and then we start working with the X1, then to X2. If we need something more, maybe X3, and only in sometimes X4 and X5. We have the pad files. This instrument is a great instrument. I love it because we can get a space into the canal before working with our rotary or reciprocation files, and we can work safe because we have a space where the file can work easily without any problems, and the shaping is a lot easier. So the path files is an interesting instrument that prepare the first part of the canal before using the NiTi files inside the canal. It's like, for example, if we get a car, a Formula One, and we use it in the country, the Formula One is going to brake really fast because it's a car done for going in the highway, but not in the country. This is the same for the files. If we use a NiTi file, we can use it into movements, in rotation or reciprocation. If we use it without a previous space, a glide path, the file is going to suffer a lot torsional stress. So we can decrease this a lot working first a glide path, in this case with the path files, and then after making this space we can go with the Formula One. In this case the Formula One is our rotary or reciprocation NiTi system, and we can use it really easily and without any problems, and we can reduce a lot the torsional stress into the canal. So it's like if we use the Ferrari car in a road or in a highway, is the fastest car in the world. But if we use it in the country, it's going to brake really fast. We can also include a ProGlider. Instead of the two path files, we can use the ProGlider file. It's the same, we change two files for one. I love the ProGlider because it's just with one instrument we prepare the road, the highway for our Ferrari, in this case ProTaper Next. ProGlider is a really nice instrument, and in wire, alloy, a square cross section with a semi-active tip. Is done only in a tip of 16 to taper. It's a variable taper also, an active part of 18 millimeters instead of 16 as the rest of the files we know. Maximum flute diameter at 18 of 0.985, in 16 0.82, a handle small as ProTaper Next of 11 millimeters. It comes in blisters sterilized of 3 or 6 files, and we can get it in 25, 21, 31 length. And as the ProTaper Next, it is thought to use it as single patient use, intended single patient use. We should use it in 300 rounds per minute and 2 Newton per centimeter. Here we have a few pictures of the ESM microscope. We can see the tip, we can see the square cross section. Here the blades also. Smaller handle, bigger active part, and only 16 tip. We can use also with the system the SX if we want to enlarge or make it bigger the coronal part of the canal, because we want to do vertical condensation or whatever. We can use it. We don't need it, but if we prefer a bigger coronal enlargement, we can do it bigger, but we don't need to use it. Here we have the 5 files. For shaping, we always need the X1 and the X2, and optional, if we want to do it bigger, the apical preparation, we can use X3, X4 or X5. We can make the obturation with gutta core. We have a gutta core of the same sizes of the prototype next files, and this is how we use it in a treatment. First of all, we have to do the pre-flaring. We have to open the access cavity and the access to the canal, so we have to reduce the interference in the entrance of the canal. We can do it first with a pad file or with a proglider, just to the middle or just to the when the file doesn't go easily to length, we can stop there and then we can use an X1. So first going to the coronals 2/3 with the proglider or with the pad files, and then we go to this coronal 2/3 with the X1. So with this movement we are going to open the access cavity to the canal, and it's going to be easier than to do patency into the canal. So we can, after this, we are going to make it bigger. We can do the patency easily. In this moment, we can get the working length also with the apex locator. And this is the video. Here we have the access cavity. We are just scouting the canal with the 10 file, the 10 hand file, and with an XX we are open making the profiling of the canal. After the profiling, we can establish working length and also confirm patency. And in this moment, we have to create a glide path in the canal for the Ferrari. In this case, the X1 of prototype next. We verify glide path firstly with the 10 hand file, and after the 10 hand file we use, in this case, the proglider. With the proglider we create this highway for the X1. After the proglider we create this road for the X1, and after the proglider we establish working length also with the apex locator, and then we have a highway to use the X1. We use it, this one, we have to use it brushing against the canal walls to create a space, to create a taper for the next file. This is a really tiny, a really small file, so we can use it perfectly. We can brush, we can go in and out without any problem because this file is really small. In this video we can see how using an X2 in the video we are brushing also. I think with this file, with an X2, it's better not to brush because we have a 2506, is enough material, enough nickel titanium to make a small transport. I know this is a really narrow cross section, small, is flexible, but if we avoid this brushing movement, we are going to reduce canal transportation. We can do it with the X1 as much as we can, but or as we want, but with the X2 we have to go just to working length and out, maybe a second time working length and out, but not many movements in brushing because this file has enough material to transport into the canal. Here we have the canal. We gauge with a 25, the 25 loose, So we have to increase the apical portion. We have to use an X3 in this case because the apical part is bigger. So we have to do apical enlargement, in this case with an X3. I advise you also not to brush with X3, just go to working length. Here is the obturation, in this case with Gutacore. This is a fantastic video performance by Clifford Rabel. Really nice video to explain you how to use it and to do a treatment as this one I did some time ago. So this is the end of the lecture. It was a pleasure to do this lecture. Thank you, Rui, for the invitation. Thank you, the masters. Thank you, all my partners. And I hope you enjoy with all these lectures.